We will continue with writing our queries to the vector database, and we have to do our imports. This imports the Qdrant class from the QdrantClient package. QdrantClient is the main entry point to interact with a Qdrant database and allows operations such as connecting to a Qdrant instance, adding, updating, and deleting vector and their metadata, querying vectors using Similarity search. Next, this imports the PointStruct class from the QdrantClient module. A PointStruct is a structure used to represent a vector in Qdrant. It typically includes ID, a unique identifier for the point, can be an integer or UUID, a vector that is the actual high-dimensional vector, a list or array of numbers, a payload that is an optional metadata associated with a vector, for example, a dictionary with additional info. This imports the UUID class from Python's built-in UUID module. A UUID stands for Universally Unique Identifiers, or commonly used as unique identifiers for data points. They ensure that each vector has a globally unique ID, avoiding collisions in large distributed systems. Next, we will build our first function, generateVector. That function accepts a single parameter description of type string, and we have to convert it in vector type. That part converts each character in the description to its Unicode integer value. Then we normalize the Unicode integer value to a range of 0s and 1 by dividing by 255. That applies the normalization step to every character in the description. Produces a list of normalized values, one for each character in the string. And then we slice the list to ensure the vector has at most 300 elements. And we check if the vector length is less than 300. And extends the vector by appending zeros to make its length exactly 300. And that line outputs the debugging information to the terminal. And that shows the first 5 elements of the vector for a quick preview. Next, we convert the vector into a NumPy array with a data type of float32. Using float32 ensures consistency and reduces memory usage compared to the default float64. ToList converts the NumPy array back into a Python list. Returning a list is often more compatible with systems that don't natively support NumPy arrays. Before moving on, I want to apologize. These are actually services features and not a repository. I had to restart my computer in the middle of the video, and instead of repository, I start with the services, but in the repository file. I apologize again. I will transfer the code later into the services.py. Thank you. Our next function is processItem. That accepts one parameter, item of object. Then we call the generateVector function with the description attribute of the item as input, and we receive the numeric vector representation of the description generated by generateFunction from above. Next, we check if the item object has an ID attribute and whether it has a value. If the item ID exists, it will be used, otherwise a new unique identifier is generated using UUID4 and converted to a string. After that, we call the saveVector function to save the generated vector and the associated metadata. Item dict converts the item object to a dictionary, likely containing all of its attributes as key value pairs. And then we return the value of success to indicate whether the entire process was successful. And our final function in the services, not repository, but it will be moved to the services, is generateID function. That is very simple function actually. Its sole purpose is to generate and return unique identifier. So let's move our services features into the services file. And we will start with our repositories. These imports I will fix a little bit later because we need to import some of the saveVector function, I think, and there are a few small changes that we have to make here, but I will do them a little bit later. So now we can start with our repository features. Let's take our imports from the services, because these imports are for the repository and we already discussed them. So we have a Python client for interacting with the Qdrant vector database. We specify the URL where the Qdrant server is running. In this case it's hosted locally on port 6333. And this is the instance Qdrant client that will be used to send commands to the Qdrant server, creating collections, adding vectors, and etc. Next line, we define our function createCollection. Its purpose is to check if a specific collection, in our case metInsights, exists in Qdrant. If not, it creates a collection. A type block begins. It is used to handle potential errors that might occur during the execution of the code inside the block. With this line, we query the Qdrant for a list of all existing collections and returns an object containing metadata about the collections. Next, we iterate over the list of collections and accessing the name property of each collection object and storing it in the collection's names. After that, we are checking whether a collection name metInsights exists in the collection names. If the collection exists, a message is printed to indicate that no further actions are needed. But if it doesn't exist, then we call the Qdrant API to create a new collection. We specify the name of the collection as metInsights. We configure the collection with size 300. That means the vectors in this collection will have 300 dimensions. The distance Cosine specifies the similarity metric to be used for searching, Cosine similarity, and we print a message that confirms the collection was created successfully. That line catches any exceptions that occur in the type block and prints an error message with details about the exception. Using distance Cosine in your vector configuration tells Qdrant to measure vector similarity based on the angle between vectors, making it ideal for high-dimensional, sparse, or semantic data where direction is more significant than the magnitude. In our app, Cosine Distance ensures that our similarity comparisons prioritize context or relationship over magnitude, making it ideal for medical insights queries, document embeddings, and other semantic search applications. This aligns with the use case where vector direction, not magnitude, drives meaningful comparisons. Qdrant supports other similarity metrics such as Euclidean distance, measures the straight line distance between 2 points in a multidimensional space, reflecting their absolute difference in a position. The dot product measures the similarity between two vectors by calculating the sum of the products of their corresponding components, emphasizing both their directions and magnitude. And there are other similarity metrics too, such as Hamming, Manhattan, Chebyshev distance, or Jacquard similarity. But Cosine, Euclidean distance, and the dot product, those are most common and they are supported by Qdrant. I will make a special video on vector databases at some point.